ancient Greek and Roman civilizations are famous for their great thinkers. Names like Plato, Aristotle, and Pliny still pepper chemical textbooks today as examples of attempts to understand their universe come to bear on modern science. As great as these thinkers were, we can't truly call them scientists, since they did not use the scientific method of discovery, observing a system, altering that system carefully, and observing again as a means of testing hypotheses. What these great historical minds did do, however, was pave the way to scientific thought by trying to rationalize their observations of the world around them. Aristotle may be the most famous of all for some of his theories regarding matter, and one of his greatest contributions to that end comes to bear on today's discussion. Because they did not participate in or manipulate the systems they studied, ancient thinkers from all over the world were confined to the study of naturally occurring materials. This fact is attested by some of the chemical terms that we use even today. For example, the Latin word for wine, vinum, is the root for the term vinyl, which was adopted in the mid-1800s as a chemical term meaning having two carbon atoms. There are so few examples of truly pure materials in nature. Just take a look around you and you'll see again and again that most of what we use today aren't pure substances at all, but mixtures of materials. This is true regardless of phase. For example, the gold we use to make most jewelry isn't really pure gold. It contains various amounts of silver, copper, nickel, zinc, and other metals mixed in to give it greater hardness. As I've already mentioned several times, the fuels that we rely on to get us around, like gasoline, aren't pure either. Gasoline is not pure octane. It's a mixture of different types of molecules containing hydrocarbons. Even the air that we breathe, though mostly nitrogen and oxygen, also contains argon, water vapor, carbon dioxide, and other gases. The water that we drink isn't really pure either. No matter which type of fancy filter or source you might be using, that bottle of water contains not only water, but ionized salts and other materials dissolved in it. Yet, when we think of these materials at the macroscopic level, we think of them as being just one uniform material. We can do this because although all of these examples, 18-karat gold, gasoline, air, are mixed intimately at the molecular level, the components are so evenly distributed within the sample that from our perspective, it's one uniform substance. A substance with properties all its own, distinct from each of the components that comprise it. In all of these examples, there is no chemical change to any of the components. We simply mix them all together into a uniform, homogeneous material. You probably noticed that in some of our previous lectures, I was careful to point out that we were investigating the, quote, principal component of certain substances. Now, I chose those words very carefully because although we can get pure gold, octane, water, or nitrogen by industrial or chemical means, they are almost never encountered in such pure states in our everyday world. Natural materials and man-made products alike are almost always mixtures of many ingredients. Today, we're going to correct this oversimplification. Today, we're going to discuss solutions. So let's begin our discussion by defining exactly what a solution is. I already alluded to this during the introduction. A solution is any homogeneous or uniform mixture of two or more substances. That homogeneity has to be at the molecular level for a material to truly be considered a solution. We encounter solutions every day, and a wide array of professionals from chefs to pharmacists to engineers create solutions that are used to make our everyday lives better. When discussing solutions, we call the more abundant phase into which other materials are dispersed the solvent, and all of those materials that are dissolved are often called solutes. Most of the time, these definitions are adequate since there is usually one overwhelmingly prevalent solvent, like the water in a cup of coffee or the turpentine used to clean paint residue. This isn't to say that we can't imagine situations in which these two can get a bit muddled. It can get complicated in cases like a bottle of vodka, which is about half water and half ethanol. Or take an example of a solid solution like gold alloyed with copper or another metal. These ratios can be very, very close to half and half. Although these are still considered solutions, the role of solute and solvent can be a bit tough to define. So we're going to stick today to more cut and dried examples in which the solute and solvent are more easily distinguished. Moreover, although solids like metal alloys and gases like our atmosphere also meet the strict criteria of solutions, we are again going to confine our discussion to liquid phase solutions, by far the most commonly encountered solutions in chemistry. So solutions are made by mixing at least one solute into a solvent. That leaves one very big question when preparing a solution. When we're dealing with a pure material, there is just that material to consider. Gold is always made strictly of gold atoms. Octane made strictly of C8H18 molecules. But when we take the step up to solutions, things change. If we're dissolving one material into another, like our example of salt into water, there comes a question of proportions. Just how much salt has been dissolved into the water? There's a continuum of ratios among solutes and solvent. And we're forced to define this relationship if we want to discuss a very particular solution. Don't think that's an important question? Just ask a doctor who's trying to rehydrate a patient with an IV of saline solution. The salt concentration in these commonly used medical products can mean the difference between life and death for a patient. Very soon, we're going to get to acids and bases and learn how varying the concentration of other solutes can turn delicious condiments into deadly corrosives also. But first, we have to understand concentrations better. So let's investigate that now. As chemists, we'll need to communicate exactly how much of each component of a solution is present. But what values should we use? Mass is easily measured in the lab using balances, so expressing concentrations in units of mass might be helpful. Similarly, we can measure volume very easily using graduated cylinders, for example. So there may be times when volume is a good choice to be included. But when molecules react, it's their stoichiometry that becomes most relevant. So depending on the discussion, we might want to use moles somehow to convey how much solute is present. So we have lots of options for reporting concentration, and several different units of concentration have become popular among chemists. Each unit has its own benefits, and we'll use quite a few of them as we proceed through the course. But for now, let's focus on learning some of the most common units used to express concentration and how we can convert those units from one to the other as needed. Expressing concentration is so vital to discussing chemistry. And yet there are so many different ways to do it. Maybe that's why it's so vital, because it's such a useful tool. We're going to talk about just a few different ways to express concentration right now in solutions. And keep in mind, there are others, but these are some of the more commonly used expressions. The first of those is molarity. And the molarity is the moles of solute in a solution divided by the total volume of that solution in liters. This gives us a very easy way to combine the number of moles of something, which we might need to know, for example, for a stoichiometry problem, with a quantity that we can actually measure its volume. So molarity really helps me in the lab when I want to get a certain number of moles of solute delivered. I can then just measure the volume. There's another unit of concentration that's often confused because they sound so similar, and that is molality, reported as a lowercase italicized m. The molality has to do with the number of moles of solute divided by not the liters of solution, but the kilograms of the solvent in which it is dissolved. We don't typically use molality in laboratory procedures because it's difficult for us to measure how many kilograms of a solvent we've got when it's contaminated, if you will, with the solute itself. Rather, molality is going to help us in the future to describe some very interesting properties of solutions. But molarity and molality aren't all there is to expressing concentration. Sometimes we need to know the mole fraction, or the relative number of moles of the solute divided by the total number of moles of compounds or molecules or atoms in a solution. Again, mole fraction is often used like molality. It allows us to predict certain properties of solutions. It's very rare that you would see this in a procedure, for example, in a laboratory, because who wants to sit at the bench and count out how many moles of solute they have, right? We don't have tweezers small enough, and we don't have enough time. So the molality and the mole fraction, again, are tied more to predicting physical properties, whereas molarity is what we usually see procedurally. But that's not all. There are even more. We sometimes report solutions as mass percent. A mass percent unit is simply the mass of the solute divided by the mass of the solution, of course, times 100 to make it a percentage. So think of it like a mass fraction or a mass ratio, if you will, multiplied by 100% to make it a more useful, manageable number. We're all very familiar with percentages. So mass percent is a very nice way to practically report on how to create a solution because, again, masses are things we can measure in the lab. But consider the fact that solutions can become very, very dilute. And when they do so, things like mass percent may produce very, very small numbers that aren't that easy to work with. Now, when that happens, we often turn to a different type of expression, an expression that we can sort of modify to our own need. And that is what I call here parts per fill in the blank. You get to choose. In this type of a nomenclature for concentration, we use the ratio of the solute mass to the total solution mass, but then we multiply by whatever number gives us a reasonable quantity to work with. So this type of a unit can manifest itself as parts per thousand, if I use 10 to the third, parts per million, parts per billion, or we could even go to parts per quadrillion, whatever it is that makes sense. Now, typically, solutions that we are interested in will fall into one of these three categories. So you'll usually see parts per thousand, million, or billion used in this way. So let's do a little bit of work with some of these concentration units and think about how we can convert from one to the other depending upon our needs. And we're going to do this with an object lesson. Let's work a problem. Seawater has a density of 1.027 grams per milliliter, and it's comprised primarily of sodium chloride and water. So we're going to treat it as though it were a solution of pure sodium chloride. What is the molarity of a solution that's 3.5 mass percent sodium chloride? Now, to answer this question, let's start at the beginning. What do we know? We know that we have a 3.5 mass percent solution of sodium chloride. And of course, the next thing we want to do is think about where we want to go. We want to know how many moles of sodium chloride are in a liter of the associated solution. So, how can we navigate this problem? Well, let's begin by acknowledging that mass percent breaks down to 3.5 grams of sodium chloride in 100 grams of solution. This gives me a good place to get a foothold for my calculation. Now I need to set about altering those units, turning them into what I'm after here. I'm going to use my density, 1.027 grams per milliliter, which is also 1,027 grams per liter. Now I chose that number because I want to be sure that at the end of this calculation I've got liters of solution in the denominator, and that's accomplished when I use liters of solution, not milliliters, for my density. Quick unit analysis, I've gotten rid of that grams of solution that I don't want in my answer. But I still have to worry about my sodium chloride expression because here I want in moles, whereas at the beginning we started off in grams. How do we get grams converted to moles? Of course, we use the molar mass. Properly inserted into the equation so that grams of sodium chloride will cancel and moles of sodium chloride will remain. My unit analysis lets me know that I'm ready to do my math. And I get a concentration of 0.615 molar. Let's do a second one. What's the molality of lead ions in a solution that's 400 parts per million lead ions? So here we have an expression where we've recorded it as parts per million because it's convenient. It gives us a number that we can use very easily, 400. And these are typical concentrations for ions like these in natural source water. But what if we need to know the molality for our experiment? How do we get there? Well, again, we start with what we know, 400 parts per million. Then we think about where we want to go. Moles of lead per kilogram of water. Right? It's moles of solute per kilogram solvent. Let's get started. 400 parts per million means 400 grams of lead in 1 million grams of that solution. And we know that 1 gram of that solution has 0.9996 grams of water. How did I figure that out? Well, because I know that we have 400 parts per million, and that's exactly what that ratio is. Right? So this is essentially how many parts per million of water we have. Now let's do the unit analysis and see where we've gotten here. I have grams of water in the denominator. All right, let's put another term in. Let's get rid of that grams of lead. I'm going to use the molar mass of lead to cancel it out. 207.2 grams of lead per mole, being sure to divide, right, because I want my units to cancel out. Grams of lead is now out of the equation. And finally, I have to introduce a term to be sure that I don't give my answer in grams of water, but rather kilograms of water. And that relationship, of course, is 1 gram per 10 to the minus third kilograms, leading me to an equation that should report how many moles of lead ions are in that kilogram of water. In this case, 0.00193 molar. As a last problem, let's try something that's a little bit different. In this case, we're going to use mole fractions. So the question here is, what is the mole fraction of sucrose in a solution that's 5.84 molal sucrose? Now, the reason that this is a little bit different is we're going to have to break our concentration down into two different terms. Remember that a mole fraction is equal to the number of moles of solute divided by the total number of moles of solution. But molality, recall, reports on the moles of a solute per kilogram of solvent. So unfortunately, it's not going to be as simple as just multiplying some numbers together. What we're going to have to do is consider the numerator and the denominator of our concentration term independently. So let's break them down and think about them one by one. Based on my concentration, I know that I have 5.84 moles of sucrose. Well, that's great because that's exactly what I need to know. I'm already done, no math whatsoever. But that leaves me with my 1 kilogram of water. Now, how many moles are in a kilogram of water? Well, we can determine that fairly quickly because we know that there are 1,000 grams of water in a kilogram of water. This would be true for anything. And we also know that 18 grams of water is equal to 1 mole of water. That's the molar mass, which gives us units that we want, moles of water. You can complete the calculation. We get 55.6 moles of water in that 1 kilogram. So now I have moles of sucrose and moles of water. But recall that my denominator uses both of those terms. That's why I had to break my concentration apart into two different terms here. So now I'm ready to do my substitution, putting moles of solute in where they belong in both the numerator and denominator, being sure to add in the number of moles of my solvent. I can now calculate the mole fraction accurately. 0.0951 is the mole fraction, a unitless number because we're comparing moles to moles. So let's imagine that we're in that kind of situation where we're not trying to make a solution from scratch, but instead trying to dilute a solution to reach a desired concentration. Now, dilution is actually a fairly simple system to model, but we have to stop and think for a moment about how it works before we can use it effectively. Now, we know that molarity is equal to the number of moles of solute divided by the total volume of solution. So why have I written it here twice? Well, I've written it here twice because dilution is the adjustment of the volume in an attempt to manipulate the molarity, while n remains constant. What that means is that I can designate for one situation, let's say before dilution, M1 and V1. And then let's say after the dilution, I can designate these M2 and V2. But remember, dilution is the addition of only solvent. There is no solute change whatsoever, so n is constant in a dilution problem. So that means that for the same sample, M1 is equal to n over V1, M2 is equal to n over V2. I can rearrange these slightly. And in doing so, I can get my n isolated. So if I multiply through by V1 on my left equation, M1, V1 equals n. Similarly, I can do a manipulation on the right side. I can divide through by V2, and I get M2 times V2 equals n. You see where I'm going with this now? Because they both equal n, they must also both equal one another. So I can say M1 V1 equals M2 V2 for any dilution that I might perform. So how is this useful to us in a dilution? Well, let's get another object lesson here. Let's actually do a dilution problem. Let's say that I have 1.5 liters of a 5.00 molar solution of sodium chloride, but I dilute that to 6 liters. What is the final molarity of the solution after the dilution has occurred? Well, this is where my M1 V1 equals M2 V2 equation comes in handy. Because my problem specifies 3 of those 4 variables, I can create an equation in which I have my 5 molar initial molarity, M1, my 1.5 liter initial volume, V1, and also my M2 not known, but my V2 being 6.0 liters. That's my final volume. So here is one equation with one unknown. I can solve this simply by dividing through by that 6.00 liter final volume. I isolate M2 and, of course, do a unit analysis to be sure that I've got my equation set correctly. And I do. I'll get molarity from this. So I do my math and I determine that my solution, which was originally 5.00 molar, is now 1.25 molar. So I can predict the effects of dilution using this very simple relationship. So now we're armed with the tools we need to report on concentration. Molarity for solutions near standard temperatures, molality, which is particularly useful for situations in which solutions might expand or contract under the influence of temperature. Mole fraction, which helps us to keep track of how many molecules of each component are present in the solution. And finally, mass percent and related units of parts per million, parts per billion, and parts per trillion, which allow us to describe extremely low concentrations when necessary. Let's start this journey by asking the question, just how does a solid dissolve into a liquid, and what happens at the molecular level when this takes place?
We're back in Osmond Lab to start our investigation into dissolution. And we're going to do that by measuring a single property of a few solutions. That property is conductivity. And to do this, I've got a little device here that consists of some light bulbs. We're going to be looking at the top light bulb here, just a regular, ordinary, everyday light bulb. And there's a circuit that is broken here. You can see that these two wires are not touching. So in order to complete the circuit, we have to get electrons to move from one side to the other. And what I'm going to do now is attempt to close that circuit using pure deionized water, a solution of a sugar called dextrose, and a solution of sodium chloride. And we'll see how successful we are with each one. So let me begin by measuring out exactly the same volume of water into each of my 3 beakers. As you can see, I've measured exactly 100 milliliters of water into each of the 3 beakers. Now I'm going to produce 2 solutions, one of the dextrose and one of the sodium chloride. Now I very carefully weighed out 1.8 grams of dextrose and 0.58 grams of sodium chloride so that when dissolved in 100 milliliters to make a solution, those solutions will be of equal concentration. I'm going to make those solutions now. Oops, don't want to lose my sodium chloride. There we go. Of course, I'll have to stir for just a little bit to get them to dissolve. Okay. All right, and there's my second solution. So just as a reminder here, I have a sodium chloride solution and I have a dextrose solution, both of which are 0.1 molar. So let's turn our power on here and begin by trying to close the circuit and light this top light bulb using deionized water only, just a highly purified form of water. Not much is happening. And that's because actually, although we tend to think of water as being a conductive material, in its pure state it actually is not. I've just proven that. Now, I'm going to dry this off, just to be safe, that we've got a nice clean system for our next experiment. Okay, now it's time to see if adding dextrose to the water to create a solution changes that property of conductivity. So again, I'll power my system on, and I'll try to close the circuit using my dextrose solution. Well, that wasn't very successful, was it? So adding the dextrose to the water to create a solution does not significantly change the conductivity of that material. Now I'll have to clean this to be sure that I get all of my dextrose solution off. Just a little bit of DI water here. There we go. Whoops. Don't want to lose that. Okay, and then I'll dry again. All right. Now it's time to test the sodium chloride solution. So power on to my light bulb, and I'll try to close the circuit using a 0.1 molar sodium chloride solution. Now the current is able to flow and light the light bulb. Interesting. So we observed different properties of equal concentration solutions of two different materials. So now we have to ask ourselves the question, what's going on?
This very same question haunted Svante Arrhenius, the famous Swedish physicist. In 1884, Arrhenius posed a new theory to try to explain exactly how certain compounds dissolve in water and why some create conductive solutions and others don't. His theory is called ionization theory, and it's actually quite simple. In order for most molecular solids to dissolve, they must interact well enough with the solvent that they're willing to give up the attractive intermolecular forces holding them together as a pure solid, in order to interact with the solvent molecules instead, of course. Sugar can do this quite easily, dissolving molecule by molecule. As each molecule of sugar dissolves, the intact molecule sacrifices those intermolecular forces holding the crystal together, but creates many new interactions between intact sucrose molecules and the water molecules in the solvent, including dipole-dipole attractions and hydrogen bonds. But what about the salt? Sodium chloride is an ionic compound, a broad array of sodium and chloride ions held together by the attraction that their opposing charges create. There are no discrete molecules to be pulled away and surrounded by solvent molecules in this case. Instead, the ionic compound must dissociate into individual ions, creating separate charged solutes. This is exactly what happens, and it gives us an explanation for why salt solutions conduct electricity so well. Chemists call these dissolved ions electrolytes in recognition of their ability to propagate electrical current when dissolved in solution. So we just saw in our demonstration how we can prepare solutions of known concentrations by carefully measuring the amount of solute, solvent, or solution involved depending on our needs. But what happens when we need to determine the concentration of a solution that we didn't prepare? An example of how this might be relevant is the testing of products that we use every day. In my days as a pharmaceutical chemist, I spent many hours at the lab bench creating solutions from drug products that I didn't make. Now, they were made on the other side of the manufacturing plant, and it was my job to verify that they contained the amount of active ingredient that they should according to the label. Fortunately, there are many techniques available for determining the concentration of solutions. And one of the most used is absorption spectroscopy. This technique was developed by German physicist August Baer in 1852. Baer observed that the amount of transmitted light decreased exponentially as the concentration of an absorbing solute increased. He mathematically converted transmittance into a unit called absorbance by taking its logarithm, allowing him to create a simple linear relationship between concentration and the absorption of light. We're here to observe Baer's law for ourselves. And in order to do that, I built a large mock-up of a device we use in the laboratory called a spectrophotometer. Now, a spectrophotometer is designed to help us measure how light interacts with matter. So it consists always of three critical pieces. First, a light source. I'll be using green lasers, so we'll be looking at the interaction of green light with the materials inside of the second part of our mock-up here, which are these tanks. These are the cells, the compartments where I'll place the things I want to analyze. And finally, the detector, which for us will just be our eyes. We'll be looking at the beams projected onto these white plates and trying to assess whether or not there's any absorption taking place in the cells. So to begin, let me get some safety glasses on here. Since I'm using green laser light, I'll be using red glasses to protect my eyes. And let me turn the lights on, and they'll shine through these tanks filled with water and just a small amount of a dispersant so the beams are a bit easier to see. So now we have our two green laser beams, one moving through each tank. Now, I'm not going to change anything at all about this tank. This tank will show us the maximum amount of light that should be getting through if nothing is being absorbed. But to this tank, I'm going to add a little bit of ordinary household red food coloring. In fact, I'm going to start with just a drop here. And let's keep an eye on that beam and see what happens as I mix this in. So I've added a few drops of my red food dye, and of course you can probably see that the water inside the tank has turned slightly pink. But more importantly, notice that the amount of the green laser light that's reaching the plate on the far side has decreased. And the ratio between the amount of light exiting our sample tank and the amount of light getting through our reference tank is what we call the transmittance. And Bayer's law predicts that this will be an exponential relationship as we go across, that's length, and as we get more concentrated as well. And we can observe both of these effects here. You can clearly see that the green beam is much brighter when it first enters the tank, and that its intensity drops off very quickly as it moves through. Now that's the path length part of the equation. And again, if we want to check the concentration, all I have to do is add a little bit more dye. Mix that in real well. We should be able to see here that now that that extra dye is mixed in there, that the beam is attenuating even faster, and we see an even more reduced absorbance based upon the reference cell. So this is a great way to observe Bayer's law. We can see that the path length and the concentration, and of course the absorptivity or the identity of the molecule that we use, in this case food dye, has everything to do with how much light gets through. So if we know the molar absorptivity of a solute, we can carefully measure the intensity of a light beam before and after it passes through the solution, and calculate the concentration of the solute in our sample. So let's review what we discussed today. We started to think about what can happen when pure substances are mixed with one another thoroughly at the atomic or molecular level. We call these kinds of materials solutions. We define solutes as the minor component or components, and the solvent as the major medium in which the solutes are dispersed. We reviewed ways of reporting solution concentrations, including molarity, molality, parts per million, parts per billion, and others. And we saw how chemists prepare solutions of known concentrations in the lab. Next, we asked how we might determine the concentration of a solution, turning to the interaction of light and matter to get our answer. And finally, we saw how Bayer's law allows us to relate the absorption of light by a sample to that sample's concentration. In our next lecture, we'll investigate exactly how much solute a given solution can hold.